Ok. Bom dia a todos. Obrigado aí a todo mundo já pela presença na live da gente, né, dos seminários da pós-graduação em Física. Hoje a gente tem um seminário dado pelo professor Leonid Butov, da Universidade da Califórnia, em San Diego. Eu vou trocar agora para inglês, que é o idioma dele, certo? Então, so, good morning, Professor Leonid Butov. So, first of all, thank you very much for accepting the invitation to give us a seminar. And I will just give the audience a brief introduction about your CV somehow, or at least what I could find on the internet. So Professor Leonid Butov, he did his undergrad course in the Moscow Institute of Physics and Technology, and he did also graduate studies in the Institute of Solid-State Physics and Russian Academy of Sciences, and did a postdoc at the Walter Schottky Institute. And then he got an appointment since 2003 as a professor at the University of California at San Diego. And from 2001 to 2003, he was a scientist at the Lawrence Berkeley National Lab. He got the Karpinski Prize Fellowship from 1992 to 1993. And what else? Let me see. Yes. So his main interests, I actually invited you to the seminars exactly because of the range of publications that I saw that you have been doing over the past 2 decades, I think, they involve semiconductor physics, excitons, etc., which is something that is very important for many of the groups here who study optoelectronics and so on. But also there are some bits on Bose-Einstein condensation of excitons, and this would be also interesting for people who work also on Bose-Einstein condensates or strongly correlated physics. So I think this is going to be very useful for our department. So then thank you for accepting the invitation. I will give you the stage now, so you can start your presentation.
Okay, thank you for the invitation and for the introduction. So I will talk about indirect excitons. So this is an outline of my presentation. So I will start from a brief introduction. So I will introduce so-called spatially indirect excitons, also known as interlayer excitons, also known as charge transfer excitons and dipolar excitons, so many names. Then I will present our earlier studies of spontaneous coherence and Bose-Einstein condensation of indirect excitons. I will briefly present phenomena observed in the Bose-Einstein condensate of indirect excitons. And then I will proceed with the main part of this presentation. I will present recent phenomena which we study in indirect excitons. So I will talk about phenomena in gallium arsenide heterostructure. This will include copper pair-like excitons and excitonic Bose polarons. And then I will present our recent studies of TMD heterostructures. I will talk about exciton transport, spin transport mediated by indirect excitons, and most recent result about anomalously higher mobility of indirect excitons. So first, especially indirect excitons, I will just call it just as an indirect exciton, is a bound pair of an electron and a hole confined in separated layers. So electron is in one layer in a heterostructure, and the hole is in the other layer in this heterostructure. And the separation between electron and hole layers, it depends on the heterostructure design, also can be controlled in situ in some heterostructures. And in the heterostructures which we study, so this separation is from fractions of a nanometer up to roughly 20 nanometers. So what are specific properties of these indirect excitons? So you see these indirect excitons have built-in dipole moment, just electron charge times the distance between electron and hole. And due to that, energy of indirect excitons can be controlled as well as energy of electrons. If we simply apply electric field in this direction, then we change energy of indirect excitons by this amount, which is simply dipole moment times the electric field. And since indirect excitons are controlled by voltage as well as electrons, we can build devices which use excitons in place of electrons, so-called excitonic devices. And this is one of the activities which we do, but I will not talk about that today. I will talk about different topics which I just introduced in the previous slide. So next, because these indirect excitons have built-in dipole moments, we interact as dipoles. And this interaction, since the dipole moment is fixed, interaction is repulsive interaction. So repulsive dipole-dipole interaction. And I will show why it is important when we will talk about excitons in periodic potential and Bose-Hubbard model. Next, due to this separation between electron and hole, lifetime of these indirect excitons is very long. It's typically several orders of magnitude longer than lifetime of regular spatially direct excitons when electron and hole are in the same quantum layer. And due to these long lifetimes, indirect excitons can cool down to low temperature, below the temperature of quantum degeneracy, which I will introduce on the next slide. So why? We simply have time to do this. We have time to cool down to very low temperature, very close to the temperature of the semiconductor lattice. In contrast to direct excitons, which have short lifetime and we cannot cool down to low temperatures of semiconductor lattice. We recombine before we cool down. So next, due to the same long lifetime, indirect excitons can travel long distances. Like direct excitons typically travel distances below a micrometer, like nanometer transport. However, indirect excitons can go macroscopic distances. We observe transport over millimeter. So really macroscopic distances, and actually we control it and we can do it as long transport as we wish. Okay, so now materials platforms. So there are various materials platforms for realizing these closely separated layers for electrons and holes. So we mostly work with gallium arsenide heterostructures and with TMD heterostructures. So for example, this is in both materials platform, we can realize type 1 and type 2 alignment of the bands, and also design of the heterostructures like gallium arsenide and TMD and other materials is very similar. For example, this is gallium arsenide, aluminum gallium arsenide heterostructure. Electron is confined in this quantum well, hole is confined in this quantum well. We are separated by a barrier. Or here, for example, electron layer and hole layers are not separated, we are adjacent, but still the distance between the centers of the layers, like in this heterostructure, is about 2-3 nanometers. And similarly in TMD, for example, here you have a single monolayer of TMD separated by HBN. You see design is just the same as this heterostructure. Or this MOSI2 WC2 heterostructure, which is very similar to aluminum arsenide, gallium arsenide. Here you have adjacent layers of MOSI2 and WC2, and separation between electron hole layers is just fraction of nanometer. Okay, so then this is just temperature of quantum degeneracy. You see, as usual, it's proportional to the density of excitons, inversely proportional to the exciton mass. And because exciton mass is low, the temperature of quantum degeneracy, for example, in gallium arsenide at our favorite density, is on the order of few Kelvin. And the density we can control in situ by optical excitation, and I will show dependence on the density later. So, like we work in optical dilution refrigerator where we realize temperatures down to about 50 millikelvin. And here is just how temperature of indirect excitons in gallium arsenide changes with time. For example, we inject hot indirect excitons, then we wait, we cool down by releasing energy to the lattice, just emitting phonons. And in approximately 100 nanoseconds, temperature of indirect excitons cools down to about 100 millikelvin. You see, it's well below the temperature of quantum degeneracy, and temperature of Bose-Einstein condensation is close to this temperature of quantum degeneracy. So this way, if we have indirect excitons with very long lifetimes, on the order of 100 nanoseconds or longer, our indirect excitons cool down to the temperatures well below temperature of Bose-Einstein condensation. And indeed, in gallium arsenide, we have lifetimes like 100 nanoseconds is our favorite, but we all even have 100 microseconds, milliseconds, whatever we desire. Okay, and you see here we routinely realize exciton gas with temperature more than order of magnitude below the temperature of Bose-Einstein condensation, and therefore we study Bose-Einstein condensate of indirect excitons. So first, why it doesn't work? For some reason I cannot change the page. Aha, now it works. Okay, so first I will talk about direct measurements of Bose-Einstein condensation, which we did already some time ago. Okay, how do we do it? So we use this nice property of excitons. When we transform to photons, then their properties automatically transform to the properties of photons. In particular, the photons conserve the coherence of excitons. Therefore, analyzing coherence of photons, we analyze coherence of excitons. So this is our sample in this optical dilution refrigerator at low temperatures. Then excitons transform to photons. We collect photons and send photons to Mach-Zehnder interferometer. Each of the arms of the interferometer forms an image on the detector, on CCD. Then we shift these images relative to each other in the XY plane, so in the plane of the heterostructure. And therefore, light emitted by excitons in point A interferes with light emitted by excitons in point B. And the contrast of interference fringes just tells us degree of coherence between excitons in point A and excitons in point B. Then we increase this distance and see how the coherence drops with this distance, simply measuring the contrast of interference fringes. And these measurements directly give us first order coherence function, which is just the contrast of interference fringes. So it is shown here how what is expected theoretically, like theoretically what is expected at zero separation between A and B, regardless of just classical or quantum gas, we always observe the best coherence, like it's coherent anyway. However, if exciton gas is classical, when we increase separation, coherence drops very quickly within so-called coherence length. And this coherence length for a classical gas is just given by the thermal de Broglie wavelength of the gas. And in this system of excitons which we study, this thermal de Broglie wavelength, even at these millikelvin temperatures where we perform the studies, is just fractions of micrometers. So it's very short. What should be observed in the experiment is convolution of this first order coherence function with the point spread function of the optics, which we use in our experiments. So therefore, we should observe this dependence. So the width of the central maximum is just optical resolution of this system, in this experiment about 1 micrometer, and these are just airy rings in this experiment. Okay, and this is exactly what we observe in the classical gas. In the classical gas, we see what is expected. This is kind of, we just check what everything works properly. However, if we cool our exciton gas below the temperature of Bose-Einstein condensation, then this coherence spontaneously emerges. Spontaneously, it's not why spontaneously? Because it is not induced by the laser. It appears spontaneously. The laser is non-resonant, separated in space, so it's completely doesn't come from the laser. And this is what is expected. Black curve is not just a schematic, it's a expected coherence, first order coherence function for exciton condensate. And the only one fit parameter is the number of particles in the k = 0 state. And we can see it fits very well to the experiment. And by this fit, we just determine how many particles we have in the condensate. And this number in our experiment is about 5,000 excitons at k = 0 state. So it's a relatively good condensate. And coherence length, like in here, it's about 7 micrometers. In our best experiments, it reaches 10 micrometers. So it's actually very long coherence length, like in the best atomic Bose-Einstein condensates. And this is direct measurements of Bose-Einstein condensation. Like there are many measurements where people claim Bose-Einstein condensation, but let's say not all of them or most of them are not related to Bose-Einstein condensation. But this is direct measurement of Bose-Einstein condensation. It directly gives distribution in momentum state, in momentum space. We simply take Fourier transform without any, let's say, work on liquid data, simply Fourier transform of this first order coherence function, we obtain distribution in momentum space. Like for a classical gas, it's classical Maxwell-Boltzmann distribution, and for Bose-Einstein condensate, so this distribution is strongly condensed. You see it's much more narrow distribution in momentum space than for a classical gas, and it's very high value. So you see it's normalized. In fact, this is like 5,000. It's a condensate with 5,000 particles at k = 0 state. And furthermore, so you see this black line presents distribution. It's a thermal distribution for a thermally distributed gas. It's not like a laser where distribution is non-thermal. So here distribution is thermal distribution, which is characteristic of Bose-Einstein condensate with 5,000 excitons in one state k = 0. So this is like this long coherence length, and condensed distribution momentum states gives us what we have Bose-Einstein condensate. So let me just list these measured properties of Bose-Einstein condensate. So first, we directly measure occupation of k = 0 state. So this occupation, and it is 5,000. Then next, we see what the distribution in momentum space is condensed. It's very narrow. Next, we measure very long coherence length, and coherence length achieves 10 micrometers, so it's very long. And finally, distribution in momentum space and first order coherence function just correspond to the theory of Bose-Einstein condensation of equilibrium bosons. Okay, so if we observe Bose-Einstein condensate, we also observed a range of phenomena which are observed only below critical temperature of Bose-Einstein condensation, just where this spontaneous coherence and condensation are observed. We also observed a set of phenomena. All of them disappear at temperatures above critical temperature of condensation. So first is this macroscopically ordered state. So this is really macroscopic length. This is like about 400 micrometers. And this pattern of exciton emission appears, as we actually verified, due to the Bose-Einstein condensation, namely due to the Turing instability in the degenerate Bose gas of excitons. We observe this Turing instability, which leads to periodic array of exciton bits. So here we published experiments, here we published theory, and theory is based on the Bose-Einstein condensation and is in a good agreement with the experiment. Next, the commensurability effect. So it shows that these bits are not independent. In fact, they form one collective state. And this state may be stable or may be unstable depending on how many of such bits we have on some confined segment, which we confined by using so-called localized bright spots. And again, theory of this Turing instability is in a good agreement with the experiment. Next, we observe spin textures. So if we create excitons here and excitons move in all directions from the excitation spots, then we observed these spin textures. For example, this is like in linear polarization, blue is vertically polarized, yellow is horizontally polarized, and you see here vertically, horizontal, we have a vortex of linear polarization. Or we observe different patterns, like this is circularly polarized, sigma plus, sigma minus, sigma plus, sigma minus. So this is four-leaf pattern of circular polarization. And we observed a variety of polarization textures, and all of them appear in the Bose-Einstein condensate, and we described in the same work both experiment and theory is in a good agreement with the experiment. It just explains these patterns by ballistic transport of excitons. Why ballistic? Because it's superfluidity in the condensate, and coherent spin precession. And this forms these observed spin textures. Next, we observed this, you see this change of the phase. So this change of the phase of interference fringes tells us about change of the phase of indirect excitons. And again, so we use similar theory, and we showed what this change of the phase is just the Pancharatnam-Berry phase in the exciton condensate. And again, good agreement of theory and experiment. Theory is also in the same work. And next, we studied so-called interference dislocations. You see this fork in the interference patterns. And actually, these forks, we showed what typically if people observe forks, we attribute them to quantized vortices. We showed this is not the case in this system. So these forks appear due to the Moiré effect in interference pattern. And we showed what the theory is in a good agreement with the experiment, and the theory is built on this coherent or superfluid transport of indirect excitons. So everywhere, theory is in a good agreement with the experiment. So these are all already relatively old works, so I will not discuss them. I finish my introduction here, and now I start talking about something recent. First, this is published like 3 years ago, Fermi singularity and Cooper pair-like excitons. Okay, so this is the predicted phase diagram for excitons, predicted by Keldysh and co-workers. So if we consider low densities, what means low? That separation between excitons is much bigger than their Bohr radius, then excitons are hydrogen-like particles, and we experience regular Bose-Einstein condensation below critical temperature. So these excitons are called hydrogen-like excitons. They are similar to hydrogen atoms. However, if we go to higher densities, when distance between excitons is smaller than the Bohr radius of excitons, then it is not possible to form hydrogen-like excitons. Instead, we have so-called Cooper pair-like excitons. I will show schematic on the next slide. And these Cooper pair-like excitons form BCS-like condensate. And when the different theories predict different scenarios, how a system transforms from low density regime to high density regime, like Keldysh and co-workers predicted smooth crossover. And this is actually, as I will show on the next slides, it is what we observed. Okay, so now a few words about these Cooper pair-like excitons. So this is conduction band, this is valence band. So this illustrates the Fermi level of electrons, this illustrates Fermi level of holes. And if you take electron at the Fermi level of electrons and a hole at the Fermi level of holes, we can form these so-called Cooper pair-like excitons. So it's similar to Cooper pair, where two electrons, both from the Fermi surface vicinity, form a pair, a bound state. Only in Cooper pair it's due to electron-phonon interaction. So here this exciton pair is due to electron-hole Coulomb interaction. It is actually similar to so-called Mahan exciton, only Mahan exciton forms in two-dimensional electron gas when we have many electrons, so we have Fermi energy of Fermi level of electrons, and only one hole. Then this electron from the Fermi level can form a bound state with hole, and this hole is called Mahan exciton. It's also exciton at the Fermi edge. However, Mahan exciton is just a single exciton in the gas of electrons, but Cooper pair-like excitons appearing in the neutral system, and we actually form BCS-like exciton condensate. Okay, so first we need to realize this ultra-cold electron-hole system, and we use the same approach. So we use the plasma of spatially separated electrons and holes. Due to the same spatial separation, these electrons and holes can cool down below this temperature of BCS condensation and form these Cooper pair-like excitons. And when we observe these Cooper pair-like excitons in the experiment as follows. So if we have a classical gas, then we have typical photoluminescence of plasma, and we fit it the shape, it fits very well by the shape of the plasma. However, below critical temperature, you see at the Fermi level, and this is just energy of Fermi level, so this enhancement of photoluminescence appears. And this enhancement occurs at the Fermi edge due to these Cooper pair-like excitons. So this is just evidence of Cooper pair-like excitons which appear at the Fermi edge of the system. And when we changed the density and realized the transition from hydrogen-like excitons at low densities, you see these hydrogen-like excitons are characterized by narrow spectra, like line width about half of milli-electron volts. And when we increase density, we have, and you see this is a smooth crossover from this narrow line characterized for hydrogen-like excitons to this broad line with the enhancement at the Fermi edge, which is characteristic of Cooper pair-like excitons in the plasma. And you see this is a smooth crossover, which was originally predicted by Keldysh and also developed by Nozier and co-workers, like this smooth crossover from hydrogen-like excitons to Cooper pair-like excitons. And overall density shift, it just gives us this good estimate for the density. So here I just indicated densities of this electron-hole system. A question? Okay. Next topic, excitonic Bose-Polarons. It's also a recent paper. So what are Bose-Polarons or Fermi polarons? If we have a mobile impurity which can move in a gas, and if it is surrounded by Bose gas, then this mobile impurity forms Bose-Polaron. If it is surrounded by degenerate Fermi gas, this impurity forms Fermi-Polaron. So this was studied in ultracold atoms. Now, recently people started studying Fermi-Polarons when we simply have exciton surrounded by degenerate Fermi gas of electrons. And when we studied, like in many works, both experimental and theoretical, with Fermi polarons. So we study both polarons. So direct exciton, this is spatially direct exciton, plays the role of mobile impurity. And Bose gas of indirect exciton just plays the role of degenerate Bose gas. And when we studied with Bose polarons, which are formed by direct exciton, dressed by excitation of degenerate Bose gas of spatially indirect excitons. And the density of direct excitons typically 5 to 6 orders of magnitude smaller than the density of indirect excitons, so therefore it's just model system of Bose polarons. Okay, so this is how it's realized in the experiment. Again, in one quantum well we have whole gas, in the other quantum well we have electron gas. In emission, we just see this emission of this degenerate electron hole system, and these Bose polarons appear in the absorption, where we create direct exciton, which is surrounded by these excitations in degenerate Bose gas of indirect excitons. And there are two types of Bose polarons. So-called repulsive Bose polarons, we can think about this as direct exciton surrounded by indirect excitons, and so-called attractive Bose polarons. We can think about attractive Bose polarons as IX, DX by exciton, bound pair surrounded by Bose gas of indirect excitons. Okay, and this is what we observed in the experiment. Like this lowest energy peak, like this peak corresponds to attractive Bose polaron, this peak corresponds to repulsive Bose polarons. We both shift Wick energy, and the energy difference between these attractive and repulsive Bose polarons increases Wick density. And when we developed theory of these Bose polarons, and we have a good agreement between experimentally observed splitting between attractive and repulsive Bose polarons and the theory. Next, if we go to zero density of indirect excitons, then repulsive Bose polarons will transform simply to direct exciton. And the attractive Bose polarons simply will transforms to dxix by exciton, where for energy splitting between them should just transform in the limit of low density simply to bi-exciton binding energy. And we can follow at very low densities. So this splitting between the lines, we calculated energy of this dxix bi-exciton, and there is a very good agreement between calculated bi-exciton binding energy and the splitting between the polaron energies in the limit of low densities, as expected in the theory. So next, we can see two sets of the lines. So the first set corresponds to heavy holes in gallium arsenide. The second set corresponds to the light holes in gallium arsenide. And for light holes, we also observe attractive and repulsive Bose polarons, and energy splitting between them also increases Wick density, also according to the theory. Next topic, which is more recent, we already published the experiments on this archive, and we are close to completing development of theory of that. When we will develop, we will update the archive and submit it for publication. So this is Mott transition in Bose polarons. So this is from the previous slide. You see, we see these Bose polarons both for heavy holes and for light holes. But if we increase density, we can go to the region where we have no Bose polarons. You see, this is simply step-like two-dimensional density of states observed in the absorption. No polaron states. And this disappearance of polarons with increasing density is just due to the Mott transition. So we measured the phase diagram in coordinates density and temperature. You can see here we observe these Bose polarons and at higher densities they disappear. And these are cross sections of this phase diagram, and we can see disappearance of both polarons is very sharp. You see we change density only by 20% and we essentially vanish. So it really looks like very close, like a phase transition. And so far these phase transitions were studied actually first by Mott, and but in a system of the same particles, let's say same excitons or maybe same atoms. When we increase density of, let's say, atoms, then at some critical density, which is now called the Mott density, so these atoms dissociate to free electrons and free ions. And Mott estimated this density for the Mott transition occurs in this range. We study a different type of the Mott transition. So here you see all particles are the same, let's say atoms or excitons. But here we have Mott transition in a system of two kinds of particles. Direct excitons here disappear due to the interaction with indirect excitons. So it's a little bit different kind of the Mott transition. This is why we are still working on development of the theory, but hopefully like within a reasonable time we should be able to complete it, and when we will try to update this archive, which so far has only experiment, and when maybe proceed with the publication of these results. Okay, now I switch to TMD heterostructures. So this is this materials platform, and I will talk about, we study both this type 1 and type 2. I will talk about type 2 heterostructures. So why TMD heterostructures? Like obviously binding energy of indirect excitons in TMD heterostructures is much bigger than in gallium arsenide heterostructures by 2 orders of magnitude. So therefore indirect excitons in TMD heterostructure are robust at room temperature. And you can build, for example, excitonic devices at room temperature based on TMD heterostructures, which we cannot do with gallium arsenide, where we need low temperatures. But not only that, like let's take the temperature of quantum degeneracy and simply regroup the terms, doing nothing, but simply regroup the terms. So this is just a number. So here you see its density times Bohr radius squared times binding energy. So this term is limited by the Mott transition. It cannot go beyond the Mott transition. So therefore you see the maximum temperature which can be achieved in exciton system is just proportional to the binding energy. So therefore, temperature of Bose-Einstein condensation and superfluidity, which can be achieved, maximum temperature, is proportional to binding energy of excitons. Like in gallium arsenide, what I was talking in the introduction was observed up to roughly 3 Kelvin. Since binding energy in TMD is 100 times bigger, we have potential opportunity to realize Bose-Einstein condensation and superfluidity at room temperature. So at least at high temperatures. So this was this simple prediction, and for us this is a motivation why we study indirect excitons in TMD. Okay, so first I will mention few results which we have so far. So this is like we published it 2 years ago, long-range transport of indirect excitons in TMD. Okay, so in TMD heterostructures, you can twist the layers, TMD layers, relative to each other. Due to that, we have so-called Mott potential, which was predicted by the group of Alan McDonald and Wang Yao several years ago. So the typical period of this Mott potential is on the order of 10 nanometers. And typical amplitude of this Mott potential is in the range which reached tens of milli-electron volts. So this is a nice realization of both Hubbard models with indirect excitons in Mott potential. We have periodic potential for indirect excitons, and indirect excitons repel each other, as I mentioned in the introduction. So therefore, this forms with a model system for Bose-Hubbard model. So this is nice, but what is not nice, this potential actually localizes excitons. Like, of course, everything is nice if potential is ideal, but any deviation from ideal periodic potential easily scatters excitons and localizes excitons. And many groups studied transport of indirect excitons, and typically everybody observed transport length less than a micrometer. Like record measurements achieved 4 micrometers for regular transport of excitons. Now I will show results. This was just what we published a couple of years ago, where transport decay distance of excitons reaches 100 micrometers and even more than 100 micrometers, because we have finite size of this sample, and this is maximum decay distance which we can claim just from the error analysis. So if we start at high temperatures, then transport is short range, like everybody observed, on the order of few microns. But when we cool temperature, at some temperature on the order of 10 Kelvin, transport length becomes huge. We can claim it's 100 micron and diverges. Something happens at this temperature. At this paper, we were not able to say exactly what happens, because CW measurements do not verify the origin of long-range transport. For example, don't distinguish between diffusive transport and ballistic transport. So therefore, we performed kinetics measurements of the transport. We create excitons in tightly focused excitation spot and measure how excitons move in real time from this excitation spot. So we measure the size of this excitation spot as a function of time. So how excitons expand with time, how we move from the excitation spot. And this gives us kinetics. So let me show this kinetics. Kinetics of indirect excitons was studied by many groups. And all groups observed what this size of exciton cloud increases very slowly with time. In contrast, we observed like several orders of magnitude faster increase of the size of exciton cloud. Like you can see here, scale is up to 4 squared micrometers. Here it's up to 100 times bigger, 400 squared micrometers. It's much faster expansion. Second, in the previous experiments by other groups, you see d squared increases linearly or sublinearly. And this is characteristic of regular diffusive transport. In contrast, what we observed, what this squared decay distance increases quadratically with time. And this quadratic growth is characteristic for ballistic transport or drift with a constant velocity. So excitons move not diffusively, but with a constant velocity. And now we analyzed this observed transport. So here on both 3 panels, we show the same transport. So this is less efficient transport, the same experimental data, different analysis. And here is our efficient transport where excitons move quickly. And now we used 3 different approaches. So like first 2 approaches are just elemental approaches. Like first is just diffusion. We analyze using diffusion equation. You see density develops due to the diffusion term, recombination, and recombination. And the recombination time, we measure it, so it's not a fit parameter. So you see here, diffusion is the only fit parameter. And you see it does not feel well to the data. So next we use ballistic approach. So here you see density varies due to ballistic transport. And when we have generation term and recombination term, again, recombination lifetime was measured. And when you see here, we have a good agreement. And from this agreement, the only fit parameter is velocity of exciton transport. And finally, the approach, which is a little bit more complex, but still has only one fit parameter. So this is so-called drift diffusion. So we have diffusion term, same as here. And when we have drift term, then we have regeneration term, same as here, and recombination term, same as here. And in this drift term, we have two contributions. One is drift due to this repulsive interaction between indirect excitons, and the other is due to the potential energy landscape in the heterostructure, which we also measure. So for repulsive interaction, we use mean field model. I will show it in a second. And then we have, due to the Einstein relationship, only one fit parameter, which is exciton mobility. And this way we can determine exciton mobility. Okay, so we used these three approaches and we built the phase diagram for this efficient exciton transport. And let me just show that we all show very similar dependence. We all show, like for diffusive approach, anomalously high diffusivity. Although it doesn't fit to the experiment, but we can still discuss it. Like diffusivity is more than 1,000. And these two experiments fit to the experiment. These two fits, you see, both ballistic allows us to estimate this exciton velocity, and this drift diffusion allows us to estimate mobility. So this velocity reaches 10 to the 6 centimeters per second, and mobility reaches 100,000. So it's very high mobility, orders of magnitude higher than in earlier studies. Now, so this both high diffusion coefficient and high mobility tells us that we have very long mean free time. Mobility is simply equal to mean free time. Like mean free time is mobility divided by the mass. So this is essentially the map of mean free time. And we have anomalously high mean free time. If we have anomalously high mobility, we have anomalously high mean free time. Orders of magnitude higher than earlier studies. And if we multiply this mean free time by exciton velocity, we obtain anomalously high mean free path. So we have long-range ballistic transport. Excitons move, it's interesting, excitons move in substantial in-plane potential, but we move without scattering, with very high mean free time over long distances with very long mean free path. So it's long-range ballistic transport despite very strong in-plane potential. And now actually we compare it with the theory. So first of all, you see this anomalously good transport with anomalously high mobility and mean free path and mean free time vanishes about at 10 Kelvin. So we have it here, we don't have it at high temperatures. And when you see it also vanishes at low densities and vanishes at high densities. So we have anomalously high mobility, mean free time and mean free path only at some special densities. And when we measured energy shift due to the dipole-dipole interaction, and we used this mean field estimate suggested by Yoshoka and McDonald to estimate exciton density. And this estimate tells us that for this anomalously efficient exciton transport, occupation of Meyer cell is 1/2. So when you have about 0, no transport, no good transport, 1/2, then this very good transport, the anomalously high mobility, mean free time and mean free path. And when occupation number reaches 1, then this transport also disappears. And this actually exactly follows Bose-Hubbard model, which predicts superfluidity at occupation of Meyer cells 1/2 and Mott insulator with no transport at occupation 1. And now I will compare with Bose-Hubbard model a little bit more details. So you can see that the Bose-Hubbard theory predicts critical temperature of superfluidity given by this equation, where N is just this 1/2 occupation of my array cell, and J is intersite hopping. So in the experiment, our observed critical temperature is 10 Kelvin. So if we plug to this equation, we obtain this intersite hopping 1.6 Kelvin. If we estimate amplitude of my array potential, just using very rough approximation of cosine function, which of course my array potential, especially reconstructed my array potential, is not a my array function, is not a cosine function, but for rough estimate, we use cosine function, we obtain 8 millielectron volt. And this rough estimate is close to the estimate given by these original papers of Alan MacDonald and Wang Yao. So we estimated for R and H stacking. In our system, we measured G factor, it's -16, which means what we have H stacking. And for H stacking, this theory predicts 25 millielectron volts, so it's reasonable agreement, especially keeping in mind what my array potential should be reconstructed, and of course this should have a more accurate formula than cosine function. And finally, so like as I mentioned, the entire motivation is that we want to reach high temperature superfluidity, like which by this theory, which we estimated like 8 years ago, can go to very high temperatures, maybe even to room temperature. But here we observe only 10 Kelvin. What's the difference? Like this equation, which we gave like 8 years ago, refers to the system with no my array potential. But if we have my array potential, we need to use Bose-Hubbard model, which of course gives much lower critical temperature because excitons move in my array potential. Then we have a clear recipe how to increase critical temperature for superfluid transport. We need to suppress my array potential. So we need to suppress my array potential, increase J, and in the limit of suppressed my array potential, critical temperature of superfluidity can move to this prediction which we did like 8 years ago, like theoretically even maybe to room temperature. So this is one of the directions of our current work. Just suppress my array potential and try to study transport in heterostructures with suppressed my array potential. Finally, the Mott transition. You can see if we go to occupation of my array cell equal to 1, so we lose transport. This efficient transport is lost. And this loss is predicted by the Bose-Hubbard model. If on-site interaction is higher, like 20 times higher than intersite hopping, then at occupation equal to 1, a Mott insulator should be realized when this interaction suppresses intersite hopping. And in our system, interaction is really strong enough, like estimate is like on the order of 10 millielectron volts. So therefore this is fulfilled. Like in fact, it's more than 100 in our system, or roughly more than 100. Therefore, Mott insulator should form. And indeed, we observe suppression of exciton transport when occupation of my array cell becomes equal to 1. Okay, and finally, I will say a few words about IX-mediated spin transport. Again, like this more refers to spintronics. People try to observe long-range spin transport. And actually, we used here indirect excitons as spin carriers. And when indirect excitons mediate spin transport. So it was studied by many groups, but typically it was observed spin transport on the order of 1, 2, maximum 3, 4 microns. Again, we observed spin transport with decay distances exceeding 100 micrometers. So this was published like CW measurements already a long time ago. And now we actually completed measurements of kinetics, but probably I will not present. Hopefully we will put it on archive within 2-3 weeks. Okay, so what we observed, what was published in these CW measurements. So we generate excitons by circularly polarized excitation. So we create exciton spin. And when we measure how this spin expands with time. And actually, we call it spin transport, but spin and valley are coupled, therefore it's spin valley transport. And we observed in some range of parameters that the spin decay distance exceeds 100 micrometers. So excitons go without losing their spin. And again, we built a phase diagram for this anomalously long-range spin transport. And it observed in the same range as where we observed this anomalously high exciton mobility. Like you see, it's observed below 10 Kelvin and at the occupation of my rest cell 1/2. And we even made correlation between spin transport decay length and density transport decay length. And you can see there is a good correlation. So what does it tell? It tells us that when exciton transport is improved due to this exciton superfluidity, then scattering is suppressed, like no scattering in superfluid. And if scattering is suppressed, then Dyakonov-Pirel mechanism for spin relaxation is also suppressed. No spin relaxation, then we observe this long-range spin transport. Okay, so this mechanism actually explains this long-range spin transport in exciton superfluid. And actually, this superfluid of indirect excitons gives a nice opportunity to realize long-range spin transport and, if you wish, use it for spintronic applications. Okay, so this is the summary of my talk. I was talking about this recent data, Fermi singularity due to Cooper pair-like excitons, and crossover from hydrogen-like excitons to Cooper pair-like excitons. Then about excitonic Bose-Polarons, about Mott transition in excitonic Bose-Polarons. So this is still work in progress. We already reported experiment on arXiv and hopefully will present theory soon. And then I was talking about long-range transport of indirect excitons. This was already published. And this is what we updated arXiv very recently, like a month ago. What we observed very anomalously higher mobility of indirect excitons and mean free path, orders of magnitude higher than for regular diffusive transport of excitons studied in earlier studies. And we showed what this is consistent with the Bose-Hubbard theory predictions for superfluid in Moiré superlattices. And we also studied long-range AX-mediated spin transport. So these CW studies are already published. And the time resolved studies of spin transport, hopefully we will put on arXiv within few weeks. And at the end, it's my pleasure to thank my collaborators. Okay, thank you.
Okay, thank you very much. I have already 10 questions to ask, so but let me wait for the audience here to ask questions too. Then they will ask questions in the chat, and then I can click on them, and they will pop up here in the video too, and then I can read them for you. So, let me also say that em português, então, se vocês tiverem também perguntas aí, se até quiserem perguntar em português também, tá ok, eu posso traduzir, viu? Mas aí eu mostro aqui. So we already have one question here. Let me read it for you. So the range of density in the Mott position is probably due to what? The crystal lattice pattern?
It's actually determined by the density of excitons. Like, I will say it very roughly, because in fact, the theory what we develop now, it's a little bit more complex, and therefore, I hopefully can just present details in a few weeks when we will put it on arXiv. But very roughly, if this is Bohr radius of exciton, and this is another exciton with similar Bohr radius, if you have only indirect excitons, when we approach together, when the distance between indirect excitons becomes comparable to the Bohr radius, like the coefficient 0.25 according to Mott, then these excitons dissociate. Like this electron doesn't know if it belongs to this exciton or to this exciton, so it becomes delocalized, it becomes free. And it is more complicated in our case when we have both polarons, when we have direct exciton surrounded by indirect excitons. Naively, I can say it's also when the distance between indirect excitons becomes comparable to the Bohr radius, we have Mott transition. But in fact, it is a little bit more complicated than that. And please give me a few weeks. We will try to discuss about that on the archive soon.
Okay, so just also to get a hook from this question here. So you are going to publish something with kind of a theory for Mott insulation using these Bose polarons, like excitons within the environment of electrons and so on, or? Because
no, these are
very interesting for me too. Yeah.
These are two different topics. Like Bose polarons, we observed in gallium arsenide heterostructure. So we are going to publish the Mott transition in Bose polarons.
Okay.
Right. The Mott transition we observed in the TMD heterostructures. These are similar terms: Mott transition and Mott insulator. Mott transition we observed in the gallium arsenide heterostructure, which is disappearance of the bound states. Yeah. Mott insulator, it's completely different things. It's suppression of transport due to this insulating state. And it is characteristic of periodic potential. Like imagine we have two neighbor cells in periodic potential. And a particle, in our case, exciton, can go from one cell to the other cell. But now you have competition between tunneling of this particle and interaction energy. So if tunnel is strong enough, it dominates and particle tunnels and we have good transport, superfluidity. If, in contrast, interaction dominates, repulsive interaction, then excitons don't go to this cell due to the repulsive interaction. And when you have insulator, where transport is suppressed by strong interaction. So this is called the Mott insulator. So it's similar terms, but completely different phenomenon. And this we observed in TMD in studies of exciton transport in TMD. And this is already published. So we already published that.
Okay. And also there is one student here. Thanks for the great presentation. Let me also read another question from Carlos Lenz. Carlos Lenz is also a professor here. He also has experimental apparatus for optoelectronics in an institute at Unicamp and also here at UFC in Brazil. So he says, nice work. Have you done nonlinear optics measurements as well? Time resolved at room temperature?
So yes, we did nonlinear optics. Actually, not in my lab. So this was done in the other labs, but we collaborated. And nonlinear optics is a little bit complicated because indirect excitons have very low oscillator strength. So therefore, we studied direct excitons, nonlinear optics with direct excitons, but the indirect excitons changed the state of direct excitons and provided information. Like we studied nonlinear optics of direct excitons to get information about indirect excitons. We published few papers. Like if you're interested, it is they are listed on my webpage, but we don't study that much because still we mostly study directly indirect excitons rather than direct excitons, and nonlinear optics can be applied only to direct excitons because indirect excitons have very low oscillator strength. And time resolved at room temperature, we did not do it at room temperature so far because good transport disappears already above 10 Kelvin. So therefore, we extended studies up to 50 Kelvin, where we see zero transport at 50. Oh, not zero, but just diffusive transport. And we did not go beyond 50 Kelvin. So some groups measure at room temperature, but we did not measure here. Like in my earlier studies, like what we published like back in 2018, we studied transport at room temperature. We did not observe anything substantial. We observed diffusive transport, and transport length was only 1 micrometer. But at that time, samples were very disordered, so quality was not good at all. So these high quality samples we produced only recently, and which indicated this long range transport with very high mobility.
Okay, and also still related to this question too, so you showed some results when you have this density around half, and then you have like this high mobility and also this high spin transport, right? So
yes.
So just as I'm just curious about it. So the excitons that you have, are they spin polarized or valley polarized somehow, or?
When we study just regular density transport, then we are not valley polarized. But when we study spin transport, we use circularly polarized excitation. So, and when it is both spin polarized and valley polarized, and when I call it spin transport, but it's simultaneously valley transport because valley is coupled to spin. And when we observe this long range spin transport with very high spin mobility, I can say spin mobility is huge, which we will publish soon, hopefully. Then it also tells what this is very long range valley transport and very high mobility for valley transport. Because we just valley and spin are just coupled.
And that you find in a twisted TMD bilayer, right? Or
this TMD heterostructure which we study, it's adjacent MOSI2 and WC2 in HBN cladded layers. So everything is in HBN.
Yeah, and but that is. So that's not the results that you have for condensation. Are there? Do you have also results for exciton condensates in this system too?
We did not measure this first order coherence function yet, so I cannot tell. We simply did not measure.
No, that's fine.
Yeah, so we measure it for non-resonant excitation, but this is in plans to measure first order coherence function in the conditions of this anomalously good transport. We did not do it yet.
Because what you presented is something that is this G1 measurement. That's very nice to check if you have a condensate or not. Because if you see, there is this evidence of Bose-Einstein condensates in bilayers, but they have a kind of a spacer between them. This is in the group of Kim Fai-Mak and Ji-Shan in Cornell.
Right.
And there, what they do is actually a time correlation between photons, I think. And this was I saw in conferences people debating if this is smoking gun evidence of Bose-Einstein condensation or not. And but
like my opinion is what we have no evidence of Bose-Einstein condensation. So we observe what excitons are formed, but there is no evidence what we are condensed. So if all their experiments just show what excitons are formed.
Yes, because that's the point. They have that's what the question came to my mind, because you have excitons being excited really by circularly polarized light or something like that. What they have there in the experiment, I think it's electro-generated. Like you input electrons and holes, and then they form the. It's a kind of electroluminescence. What they have is more like electroluminescence.
In fact, what I showed for gallium arsenide, we call this first order coherence function measurements. It's a combination of these two. Holes are optically excited, but electrons are electronically injected. So this is why I tell it spontaneous coherence. It's not induced by laser excitation, because electrons are electronically injected, not optically excited. And but yes, it's like many phenomena can be observed. It's a complex system. So therefore, you really need direct measurements to claim Bose-Einstein condensation. And this, like we performed these direct measurements. We just measured distribution in momentum space and showed what it is condensed. But quite frequently, something is observed and claimed as a Bose-Einstein condensation, but it may be something else. In particular, sometimes excitons simply form, but they are not condensed. So it's so in many experiments, people see what excitons are formed, but no evidence what they are condensed.
It is a controversial field for sure. Yeah. And so one more question here is, hello, thanks for the talk. Is it possible to experimentally measure the exciton's position or size or movement in a direct way? If so, how?
Position and movement we measure in a direct way. We make it time resolved and we see how excitons move in real time. Just how the excitons move in space and time. So we measure it. But we, of course, measure not individual excitons, but the entire exciton gas. So our technique doesn't allow resolving individual excitons. There are techniques which allow resolving individual excitons, but and some people try to detect single exciton wave function, how it develops with time. But so this is done with some near field measurements. Okay, this is challenging field, resolving transport of individual excitons, but people are trying to do this. We don't. We measure directly how excitons move, but it's not a single exciton, it's a exciton gas.
Yeah, and I've seen before also there are some groups in Germany, I think, where this group of Alexei Chernikov and some other collaborators, they also see this thing, but usually I see them showing diffusive behavior. I think they have one where the exciton becomes like a ring or something, but it's actually like a Gaussian distribution of excitons that gets wider in time, right?
Right. I made a reference to results of Chernikov. It was one of these works with very bad transport.
Yes.
So their transport is very inefficient, very slow, on very small distances. So, and you see our transport is
took note here
orders of magnitude better.
I'm sorry. Is that a problem?
And let me finish on your first question. And regarding the rings, maybe you noted I also showed the rings which we observed 25 years ago. Chernikov observed it a few years ago, but it's similar origin of the rings. We observed and published it 25 years ago.
Yeah, so you mean those rings where they explained somehow, I think it's based on the temperature of the excitons locally different in the middle or in the border. I think that was something...
First, there are different kinds of the rings. The rings, for example, one ring I showed today, there is also a ring. When you excite excitons, you hit the system at the point of laser excitation.
Yes, exactly.
And due to this heating, intensity is suppressed because excitons go to so-called dark states where momentum is beyond the optical cone. But when excitons travel, they cool down and we start to occupy the optical cone more efficiently and intensity increases. So we observed this and provided theory already a quarter of a century ago.
Okay. Yeah. That's what I was referring to indeed. Yes. But like I was referring to in these other recent papers. Yes, but it has been seen before then, right? Yeah. And
right, everything is published.
Yes, I see. And also, Professor Lenz also asked, like, where and when you worked with Daniel Chambla. He said that he met him at Bell Labs. Must have been some time ago then, yeah.
Yeah, thank you for this question. So I met Daniel Chemla at a conference sometime in 90s, and when he invited me to work in his group, and I was first as a special scientist, then staff scientist in Lawrence Berkeley National Lab in the group of Daniel Chemla. So I worked for 2.5 years there, from 2001 to 2003. And for example, these works on the rings, which we just discussed, were done when I was the staff scientist in the group of Daniel Chemla. And when in 2003, I moved to San Diego.
Okay. And also in this, one of the results that you showed there with the ring, you also have this so-called this MOES, this, it's a kind of...
yeah, this is what we call macroscopically ordered exciton state. Like this ring is simply homogeneous ring above critical temperature of condensation. Ring itself is completely classical phenomenon. But if we cool with temperature below the temperature of Bose-Einstein condensation, then this ring breaks into the array of bright spots. And this is related to condensation. And we explained this in collaboration with theorists Leonid Levitov at MIT and Ben Simons in Cambridge. And the mechanism is the Turing instability. Because this ring forms on the interface between electron-rich region and hole-rich regions. So simply, excitons are formed from electrons and holes. And this process of exciton formation can be stimulated like by the quantum degeneracy, like the rate of exciton formation is proportional to 1 plus n, where n is occupation factor of exciton state. Like in classical gas, it doesn't matter because n is much smaller than 1. But when you form a condensate with very high n, excitons start to form quickly. And this is positive feedback for increasing density of excitons. Okay. And when you have positive feedback, you have modulational instability. Now you have interplay between positive feedback, which tries to increase the density, and negative feedback, like transport, which tries to make everything homogeneous. And interplay between these two feedbacks determines the period of this density modulation. So this is just Turing instability. And Leonid Levitov and Ben Simons calculated the period of this wave, and it is in a very good agreement with the experimentally observed period. And also, this instability requires this stimulated kinetics due to quantum degeneracy. So this is why it appears only in the condensate, below the condensation temperature.
Okay. Oh, that is very nice. It's a very nice result.
Yeah, but that's interesting. But all this was published like almost quarter of a century ago.
I saw this picture like many times already, and also because we also are we have been working here in the group on this, like trying to find situations where you have spontaneous symmetry break of the translational symmetry of the condensate. So in supersolids, for example, or this charge modulations of or density modulations of excitons and things like that. And that's why I came to one of these results before, because I saw this is a modulation of the exciton density. Then at first I thought it could be something that, for example, if you solve Gross-Pitaevsky equation for a density of excitons like that, if you put the interactions between them somehow, then you could explain why the modulation is formed like that. But now, as you said, it's actually a kind of a different phenomenon, actually, right?
Right, because interaction is repulsive. And this repulsive interaction tries to make everything homogeneous. Yes, so this is just the competitor, like Turing instability is positive feedback, but repulsive interaction and transport is negative feedback. And competition between these two gives the period. Yeah, so it's like Turing instability worked very well. It's not only the modulation itself, but also commensurability effect. It was also explained by the theory within the same Turing instability, and again, good agreement with the experiment. So I am more or less confident that this is the nature of this phenomena. Supersolid is very interesting, but experimentally extremely challenging because, for example, something like superfluidity is robust when you create disorder, but supersolid is not, because disorder easily destroys supersolid. Wigner crystal, all these kind of collective states are easily destroyed by disorder. So at least we don't have any experimental evidence, and it is a very challenging field.
Yeah, for sure. You see, this is like even maybe more controversial, like, because as you said, many people have claims of like Bose-Einstein condensation in TMDs, for example, and now there are also claims of supersolid formation of excitons. I don't know if you saw, there are some papers on arXiv already discussing these things. There is one where they have a kind of two Corbino disks, I think, and they have some measurement where they find superfluidity, and then in the middle of the superfluid phase, they find some kind of an insulator and so on, and that's why they think it could be a kind of a crystals.
Yeah, so far I can comment on like Bose-Einstein condensation on superfluidity, but I don't have comments on supersolid simply because I did not study by myself.
Yes, okay. Yeah. So I think we are more or less done. We had already some like 20 minutes of questions somehow. Let me see. There is also one question here about, no, I think this may be a bit off the topic. It's Manuel, he is asking about if you think that carbon chains inside of carbon nanotubes could also sustain long-lived hybrid excitons. Or does the electron phonon coupling fundamentally limit their coherence? That would be a one-dimensional system, I think, right?
Right. But first of all, I should say I'm not an expert in carbon nanotubes, so maybe I'm not a good person to ask questions like that. I'm sorry.
Yes.
So I just can give a general answer, but I have no expertise in this field.
Okay. So thank you very much again for your time and for the opportunity to show us some of your results and explain them. It was a very nice presentation, very nice discussion. So if you also need some, if you want to keep any kind of collaboration with us, maybe in the experimental side, also with the group of Carlos Lenz or other groups here who do optoelectronics or Raman spectroscopy, etc. If you are interested, we can keep collaborating, or with the theoreticians like me and some other people in the group, we can keep in contact if you want. So
yeah, thank you very much for the invitation, and thank you for these nice questions. It was a pleasure to give this talk.
Okay, so I will finish the transmission right now. Obrigado aí todo mundo pela presença, viu? Até mais.